Let's look at drawing some graphs of the position, velocity, and the acceleration of an object that's in free fall. So we still have our same kinematic relationships between the position, the velocity, and the acceleration. All those relationships we learned before are still the same. The difference now, since we're in free fall, is that we know that our acceleration is a constant negative 9.8 meters per second squared. So let's look at this problem here. We're going to draw three graphs. One is going to be position, y position versus time. One is going to be velocity versus time, and one is going to be acceleration versus time. So press pause, see if you can figure out what those graphs would look like, and then press play to go through it with me. I'm going to start by drawing the acceleration graph first because that's the easiest one for me. Since the object is in free fall, remember any time that something's in the air and nothing else is touching it, we know that it's in free fall. So this object is dropped. The moment that it leaves your hand and that your hand is not touching it anymore, we're going to consider that it's in free fall. So drawing the acceleration graph is pretty straightforward. So on my vertical axis, I have the acceleration of the object. On my horizontal axis, I have the time that's elapsed. And my acceleration is constant. I have a constant acceleration of negative 9.8 meters per second squared. Anytime an object is in free fall, this is what its acceleration graph looks like. Whether it's going upwards, whether it's going downwards, whether it's at the top of its trajectory, it doesn't matter. If it's in the air and nothing else is touching it, it's in free fall and the acceleration is a constant negative 9.8 meters per second squared. Now from this acceleration graph, we can draw our velocity graph. And it's kind of easy to go backwards this way because remember that the derivative of my velocity graph is my acceleration, or the slope of this graph is my acceleration. So I want to draw a graph of something that has a slope of negative 9.8. I'm not going to worry too much about numbers, but I definitely want it to have a negative slope. So I'm going to draw something that has a shape like this, a straight line that has a constant negative slope, and that negative slope is the acceleration value. So before I draw that, I know the rough shape of the graph is going to look like this. I need to figure out where is that graph placed on the vertical velocity axis. Well, the ball is dropped. That means at t equals 0, at the moment that it's dropped, the velocity is 0. The initial velocity is 0. So what I'm going to do is draw a velocity versus time graph. So I have velocity on the vertical axis and time on the horizontal axis. I'm starting at a velocity of v equals 0, and I'm drawing a nice negative slope here, and it's a constant negative slope. That way, this graph definitely, when you take the derivative of this, you get a graph that looks like this for the acceleration. Now we're going to draw the position, and this is going to be the y position. So what I want to think here is whatever the value of my velocity is, that should be the slope of this graph. So I want to start with something that has a slope of 0. So in the beginning, I want it to have a slope of 0 and I want it to be kind of flat. Then the slope becomes more and more negative because the velocity becomes a bigger and bigger negative value. So I want to draw a picture that's going to have a slope that becomes more and more negative, more and more steep. So I'm going to draw something like this. So here I have a nice constant 0 slope in the beginning, and then you can see the slope of this line gets more and more negative and more and more and more negative, and that's when the object lands. So this is my y position versus time graph for this object. Let's do another one. It's very similar. The only difference here is that the ball is thrown downwards with an initial speed instead of being dropped. So press pause, take some time, look at the graphs you just drew, and think about what's different in those graphs. What's the same from those graphs in this case? And see if you can draw the three graphs for this problem. Then press play when you want to go through it with me. So again, I'm going to start with the acceleration graph. Nothing has changed here. It doesn't matter that in the previous example the ball was dropped and in this example the ball is thrown downwards. That does not affect the acceleration. We're looking at the acceleration the moment that the ball leaves your hands, and the moment that it leaves your hands, the ball is in free fall, and the acceleration is a constant negative 9.8 meters per second squared. That means that the graph we draw for our velocity still should be a straight line with a negative slope. The difference is that now my initial velocity is not 0, it's something negative. How do I know it's negative? Because it was thrown downwards. The velocity is in that downwards direction, it's in that negative y direction. So I'm going to start my graph, instead of starting it at 0 like we did here, I'm going to start down at this initial value, and that's going to be that initial V initial. Sorry, this is the velocity graph. I'm not sure why that V didn't show up there. But again, it still has that same negative slope just like in the previous graph, except now we're starting with some initial negative velocity. There's the V. And then for my position graph, it looks similar to the previous one, except now instead of starting with a nice flat, a little bit of a flat piece in the beginning with a 0 slope, I want to start off right away with a negative slope. So that's what you can see here. I start off with a negative slope and it still just becomes more and more and more negative. This will be the last one that we draw. Again, it's a similar situation, but in this case, we're going to be throwing the ball upwards. It's going to reach a maximum height and then fall back down to the ground after that. So press pause, again, take some time, look at the previous graphs you drew, think about what's the same in this case and what's different, and see if you can draw 3 new graphs. The acceleration graph is exactly the same. T1 is the time when it reaches that maximum height. So you can see during this part of the time, the object is traveling upwards. At this time it reaches its maximum height, and here's when it starts to fall back down. The acceleration does not change. It's accelerating downwards the whole time because it's in free fall the whole time. Even when it's being thrown upwards, even when it's traveling upwards, it's in free fall. The moment that the ball leaves your hand, it's in free fall, whether the ball's going up or down. The velocity is going to look similar in one sense. I still need to have a line that has a negative slope, but now I want that initial velocity to be positive. So here is a positive initial velocity, and what you can see is the velocity still has this negative slope that's constant. That slope is the negative 9.8, but the velocity is getting smaller and smaller and smaller. This represents as the ball is traveling upwards, it's slowing down and slowing down and slowing down. Why is it slowing down? Well, think about when you throw a ball upwards, it slows down. In terms of physics, why is it slowing down? I have a positive velocity and I have a negative acceleration. What happens when your velocity and your acceleration are in opposite directions? You slow down. That's right. So the object is slowing down, slowing down, slowing down, slowing down. At this point, it reaches the maximum height. At that maximum height, the velocity is 0 just for that moment. Nothing happens to the acceleration. And now it starts to fall downwards, and it's getting faster and faster and faster as it falls downwards, still at this same rate of the negative 9.8 meters per second squared. That's that slope. For my position graph, now what I want here is I have a positive velocity. That means right here I need a positive slope. And that positive velocity becomes a smaller and smaller number. That means I want my positive slope to get smaller and smaller and smaller. And right here at T1, I want to have a slope of 0 because that's when my velocity is 0. Now my velocity becomes more and more negative, so I see a slope that becomes more and more negative and a bigger and bigger and bigger negative value, so my slope becomes a bigger and bigger and bigger negative value. So the graph of the velocity and the acceleration don't really make sense with, if you imagine throwing a ball upwards and when it falls down, what would the graph look like? This is the graph that I hope makes a little bit of sense to you, because this is kind of showing what the trajectory of the ball might look like in time. The velocity graph and the acceleration graph might not be obvious, but what we're doing here is we're representing these values graphically, and at this point I don't think it should look obvious. I don't think it should. You shouldn't be able to look at this and be like, oh yes, that makes total sense to me, I'm a genius. At this point we're still learning. This might be super crazy and you might think, how in the world does this represent the velocity? If you're thinking that right now, that's awesome. I'm so glad you're thinking that, because it means you're thinking. Thank you for thinking. What I want you to do is not panic and give up. I want you to watch this video again. And I guarantee you the next time you watch this video, it's going to make a little more sense. Wait a few days and watch this video again, and it's going to make even more sense. And then guess what? The quiz will happen and you'll do awesome on it and you'll feel good about yourself. Okay? Do that for me. Thanks.